So now we're going to look at a pair of concepts when either we're evaluating the limit when x approaches infinity, so you're getting a really, really big number for x, or when you're evaluating the limit of a number like x equals 3, but the y value is infinity. So generally this has to do with functions going all the way to the right forever or up forever. First, we'll look at the case when the x values approach infinity or negative infinity. So what it will look like, instead of saying the limit as x approaches 3 or the limit as x approaches negative 5, you'll have this infinity or negative infinity symbol down here. And they're basically saying, imagine a number that is infinitely large. So concept-wise, they're just saying what's happening on the far right-hand side of the graph, what would happen if we went to the right forever. So one of the easiest ways to do these problems is to draw the graph, or if they've given you the graph, to use it for reference, and then just look at what's happening on the far right side of the image. There should be an x value that the graph appears to be approaching, usually because there's an asymptote, so the graph is getting closer and closer to the number for that asymptote, but it's never going to actually touch it. So if you look on the far right-hand side when the limit as x approaches infinity, you'll find the limit. Or if you don't have access to the graph and you're not able to use a graphing tool like Desmos Graphing Calculator, you could also construct a table the way we did on the first lesson, and you could just plug in a very large x number. Pick something like 1,000,000 or 1,000,000,000 even, and plug that number in for all the x values and see what you get for your y value answer. The concept is pretty much the same when they say the limit as x approaches negative infinity, just like I would say the limit as x approaches 3 or negative 3. This is just indicating that we're going in the opposite direction on the number line. So for negative infinity examples, you would just look at the far left-hand side of your graph, or you could construct a table if you don't have access to the graph, and put in a very large negative number, like negative 1,000,000, and see what the y value seems to be approaching for your answer. So here's an example I'm going to show you graphically, and we can talk about the table as well. This is saying find the limit as x approaches negative infinity. So we're looking at the left-hand side of the graph for the function 3 plus 2 to the x. This is a function you should have learned how to graph back in Algebra 2, but even if you don't remember all the rules necessarily, that's fine. I'm just going to show you the image in Desmos Graphing Calculator. So here you can see I've just typed in 3 plus 2 to the x. It assumes the y equals part. So we have our function drawn for 3 plus 2 to the x. And then remember, we're looking for what happens when x approaches negative infinity. So you can zoom out as much as you want to, but it's pretty clear on this graph that it doesn't seem to be changing much, no matter how far over or how far zoomed out I get. And if you zoom in to see exactly what this y value is, it appears to be approaching a value of 3. And by clicking on the red line for the graph, I can even see the exact decimal values as they go over farther and farther. So you can see that it's getting really, really close to 3. Technically, it will never actually hit it, even though it might eventually end up saying 3. That's just because it's only showing me 3 decimal places. So eventually it's getting so small and so close to 3 that Desmos just says it is 3. So that is our limit. That's on the left-hand side of the graph. We'll talk about what's happening on the right-hand side of the graph on a later example. So graphically, I've just shown you why the limit of this function is equal to 3, but you also could have made a table, like I said, or just plugged in an x value. In fact, if you plug in something like 3 plus 2 to the negative 1,000,000, your calculator actually can't even give you the decimal for how small the value is at that point, so your calculator will just say 3. Technically, it's not quite 3. It's something like 3.000000001, but your calculator isn't precise enough to identify that, so it'll just say 3 as well. And the reason I'm plugging in a very big negative number is because this one says negative infinity. So do keep that in mind. If it was as x approaches positive infinity, I would put in a big positive number and see what the calculator gave me. So either way is valid for determining the limit on negative infinity or positive infinity. Let's also talk about a shortcut that comes in handy a majority of the time. It won't work for every single function, but for most functions that are dealing with x approaching infinity or negative infinity, if you know your rules for horizontal asymptotes, if you remember them from algebra, then you can actually use those in most cases. So this will work for a rational expression. And if you recall the definition of rational expression, that just means you have a fraction. So there's something like 2x plus 3 divided by x minus 2. So you should have a fraction with x values on top and x values in the denominator. If you have that situation, then you can use this process. Basically, you need to compare the degree or the biggest exponent of the numerator and a denominator. It's not necessarily which one's first, although usually it's the first one. It's whichever exponent is biggest on top and bottom for the variable. If the exponent on top is bigger than the bottom, then there is no horizontal asymptote, and it's either going to be going up forever or down forever, so you would say positive or negative infinity. And we'll talk about that case more in just a moment. That's what was happening on the last graph on the right-hand side. It was going up forever, so we would have said positive infinity. If the exponents are equal, so if you have x to the third and x to the third, then you look at the coefficients out front. That's what a and b represent. So whatever number is on top divided by the number on the bottom, that is the value for the horizontal asymptote, and that will be the limit. So if your numerator is a 5 and the denominator is a 2 for the coefficients, then you would say y equals 5 halves, or the limit is 5 halves. And then the last case is for when the exponent on top is smaller than the exponent on the bottom. That's what n and m are. So if the exponent on top is smaller than the other exponent, then y equals 0 is the horizontal asymptote, or you would say the limit is 0. The y value is 0. That's where the asymptote is occurring. So knowing your horizontal asymptote rules can save you a lot of time, because then you don't have to draw the graph or plug in numbers into a table to find the answer. So I'll show you how that process works. So first things first, it's important to know when you can use the shortcut. This is what I was referring to by a rational expression. I have a fraction with variables on top and variables on the bottom. So when you're looking at the rules I gave you here, this only works for rational expressions. This is a rational expression. It only works for infinite limits. This does not work for the limit as x approaches 2, for example. This only works for the infinite or negative infinity limit values. So I can use it in this case. So notice that the exponents are the same. The biggest exponent for the variable in the numerator is 2. The biggest exponent for the denominator is also 2. So if we're looking at the way I had those labeled on here, n is the exponent on top. So I'm going to point out that n equals 2. And m is the exponent in the bottom, the biggest exponent in the denominator. So m is also 2. So when your exponents match, this is that second bullet here. I said if the exponents are the same, then look at the coefficients, a and b. So the numbers that are attached to those two x values, in this case, a is 3 and b is 2. It's the numbers attached to the biggest exponents. So my answer for this is going to be a divided by b. That is the limit as x approaches infinity of this value. And if you want to test it, you can still do it with the other methods I showed. The advantage of this is just you don't have to draw the graph or make a table. But I'm going to show you the graph as well so you can still see the visual representation of this. So we already got our answer, but here you can see I've typed the function into Desmo's graphing calculator again. And since this one said the limit as x approaches infinity, just look at what's happening for the y value as I go farther and farther to the right. So on the far right-hand side of the graph, it appears to be hitting a value really close to 1.5. And the farther out I go, the closer I'll see if I keep zooming and moving over. So 1.5 as a fraction is 3 halves. That's where that number is coming from. So it is good to recognize fractions that are close to decimal values. So now let's talk a little bit more about the cases where you're taking the limit as x approaches a number, like as x approaches 2, but sometimes you get an answer of infinity or negative infinity. So now our x value is a constant. It's a small integer like 3 usually, but our graph is going to be going up forever or down forever. So your answer equals infinity whenever you're looking at the graph and you see it just moving up, or if you're plugging numbers into a table and you're getting some ridiculously large number like 1 billion for the y coordinate. So if you ever see something where it seems to be incredibly large for the y values, it's probably going up forever. You can also do this from the table, like I said. So plugging into a table and getting an incredibly large positive number as you get closer and closer to x equals 2 or whatever your c value is, that would indicate an answer of infinity. And then the other way around, if you're evaluating the limit as x approaches 2 as an example, and you look at the graph and see that it seems to drop down forever from whichever side you're dealing with, then that would be an indication that your answer should be negative infinity for going down forever for the y value. Or if you're doing this from a table, maybe you plug in a number like 2.999 and you get an incredibly large negative number like negative 1 billion or negative 1 trillion. That would be an indication that the graph is approaching negative infinity. So we say that because there is no largest or smallest number on the number line. There's always a bigger number I could come up with. So we use the infinity symbols to represent going forever in that direction. So let's see an example of this. Here we have the limit as x approaches 7. And remember, by putting the plus sign after the number, that means that we're really interested in what's happening on the right-hand side of 7. We're not comparing the left and the right side together. We're just saying what's happening on the right-hand side of 7 as we get closer and closer to that number. And the function we're working with is 3 over x minus 7. So I'll show you this both graphically and by plugging it into the calculator. So here's the function 3 over x minus 7, and here's my x equals 7 value. So we're interested in everything that's happening along this vertical line here. Well, this problem specifically had as x approaches 7 from the right-hand side, so I'm really just looking at this piece of the graph as I get closer and closer to 7, as I approach an x value of 7. Well, it seems to be going up forever. It doesn't matter how far I scroll up, doesn't matter how far I zoom out, it just keeps going up. So in that case, I know that my answer is positive infinity. Now, if I had put a negative after the 7 instead, if I'd put 7 minus, then for my answer, I would be saying that this graph is going down forever, so negative infinity. So it is very important that you keep in mind, do they have a minus after the number or a plus after the number? So plus after it means from the right, this one's going up forever. So our answer is infinity from looking at the graph, but what if we didn't have access to the graph or didn't know how to draw the graph? We could also do this from a table by saying, all right, well, this one's asking us to look at the limit as x approaches 7 from the right-hand side. So a number that's on the right of 7 would be something like 7.00000001. So what if we evaluated 3 over 7 point, and we're picking a number that's just barely on the right-hand side of 7. This number is just barely on the right-hand side of 7. And if you plug this into your calculator this way, so replacing x with the number really close to 7, I got an answer of 3000 and 4 more zeros. So what's happening here is I'm getting such a ridiculously large number. It seems, and I could get closer if I wanted, I could have put like 10 zeros and then a 1. It seems like the closer I get to 7, the bigger this number gets. It's not stopping or slowing down and approaching a specific value. It just keeps increasing forever. So that's our indication that this one is approaching infinity, because in the instructions I gave you here, it says when you look at a table, if the y values are incredibly large positive numbers as you get closer to the x value, then it is infinity for the answer. And if I was getting negative numbers for my answer, I would be putting negative infinity. So that's it for the notes. That's how to evaluate limits as they approach x is infinity, or how do you write your answer when the y value is getting closer to infinity.